So domain is a little funny because when we start talking about domain, your example functions that you're used to, there is never any problem. You can plug any number into x squared plus 3x. The problem is when functions start getting more complicated, you have to start watching for trouble. So at this point in your math career, we're going to be looking primarily for two things. We're going to be looking for division by zero and square roots of negatives. Zero on top is fine, zero on the bottom is bad. So 3 over x plus 5, for example, is bad when x is negative 5. And square roots of negatives, you can take the square root of 0. The square root of 25 is 5 because 5 times 5 is 25. The square root of 0 is 0 because 0 times 0 is 0. But you can't take the square root of a negative. So, for example, if you have something like this, you have the square root of a negative unless x is at least as big as 4. Okay. Polynomials, the domain is all reals. But that brings up the question, what heck is a polynomial? A polynomial is a function that has positive whole number exponents only, including constants. So let's just say has rather than is. So first, let me just give you a few examples. X squared plus 3x is typical. 2x plus 5, 5x to the 4th minus x to the 7th, whatever. You don't have to have more than one term, and you can be a constant. Not examples are things like 1 over x and x to the minus 1 or negative 2 or whatever, negative exponents, and fractional exponents, for instance, which we'll get to eventually. But yeah, negative and fraction exponents, things like that, no. Square roots, no. So if you have something like the first problem in problem 3, the first one, the domain is all reals. So how do you notate that? You say x, set builder notation says x such that x is a real number. Interval notation says negative infinity to infinity. Unless I ask for a specific notation, I don't care which. I kind of prefer set builder notation mostly because it's easier to write from what you say. This one, the denominator can't be negative 3, so my domain is anything except 3.
Negative 3. Oops.
This one, the domain is anything except 4 and negative 7, because that's where your division by 0 is. Notice that the x plus 2, don't worry about this, because 0 on top is not a problem. Okay. This one, again, 0 on top is a problem, no problem, and this can't, 7 can't be 0, so this one has a domain of all reals. 1, 2x plus 4 is 0, when x is negative 2. So this one was taking away negative 3 and 3. Square roots is where it starts to get a little more interesting. X plus 2 equals 0 when x is negative 2. I want to say, which side of negative 2 gives you nice numbers? Well, bigger numbers than negative 2 give you square roots of positives. So I want to have x to the right of negative 2. This one, square root sign, if the 2 isn't under the square root sign, it doesn't count. So it's just x to the right of 0. The plus 2 affects the graph, but it doesn't change the domain. Next problem, we have square root in the denominator. So we have to throw out the equals negative 2 as well. So we have x such that x is only strictly greater than negative 2. Can't equal because of the division. Can't be less than because of the square roots of negatives. This one's a little peculiar because you can have two things go wrong, and they're not quite the same as each other. First of all, with the square roots of negatives, you have to be x greater than or equal to positive 2. But there is one other thing. When does root x minus 2 minus 5 equal 0? When does square root thingy equal 5? When the thing under the square root sign is 25, which means x minus 2 is 25. X can't be 27. That one takes a little thinking through. Okay, so, and again, if it's not the bottom thing that you wrote, please put a circle around it so that I know that that's what you intend for the answer. Range tells you how high or low the function goes. X tells you, if you squish it onto the x-axis, what's going to be allowed. Range tells you if you squish it onto the y-axis. If you graph the function, it ends, or rather it starts at a particular number, like this. If I trace at x equals 3, I get y equals 2. And it goes down from there. It doesn't get any higher than this. So if you graph it on your calculator, you see that the range is down from positive 2. And I knew to trace at 3 because of my domain things. Okay, speaking of that, when I graph 1 over x, and we'll be talking more about this in the near future, it gets closer and closer to a height of 0. But you can't actually have a fraction. The only fraction that can equal 0 is one where 0 is on the top. So if you have 1 over x, you can't get 0 on the top. The height can't be 0. So this is why, such that y is not equal to 0. And we'll talk a little bit more about that function. That's a very important function. 1 over x squared looks kind of the same, except, what is that? The random dot. Let's get rid of that. So there was a random dot. It looks pretty much the same, except that you won't go below the x-axis. It does look like it's a function in 2 chunks. This is true. The domain can't include 0, but the range can't include 0, but it also can't include any negatives either. It only includes the positive heights. If you start, you have to start just above 0. If you graph x cubed on your calculator, you see it kind of looks like this. The right-hand side looks like a parabola, sort of, and the left-hand side is upside down, and that's because if you cube a negative, negative times negative is negative. So you don't flip it up to the positives. This has a range of all reals. odd functions, odd exponents tend to have a range of all reals.
Okay, and because it's bothering me, I said it, but I didn't write it. I'm going to put the negative in with the 3.
Set 3.
Oh, stop it. Hold on a second.